Hi, my name is Michael Farrell, and I contribute to free and open source software in my spare time. You might remember me from my work on MetroDroid, a contactless transit card reader for Android. Many governments around the world are releasing contact tracing apps for their citizens to install on their mobile phone to assist in tracking the spread of COVID-19. I've been spending my ISO time looking at how these apps work, and today I'm going to talk about the two different ways that these apps exchange data using Bluetooth Low Energy and the advantages and disadvantages of each. But first, a primer on how this all works. The basic idea is that everyone runs an app on their phone. This app exchanges a temporary identifier with other users of the app who are nearby using Bluetooth Low Energy and records it in an encounter log. If it later turns out that someone tests positive for COVID-19, there is some mechanism to use the encounter logs to notify anyone who they were near recently and to limit the spread. Now there's a lot of details I've skipped over here about encryption and who gets access to that encounter log, but these details are generally specific to each system. On a Bluetooth level, the biggest difference is whether these systems exchange temporary identifiers using the generic attribute profile, or GATT, or exchange it using beacons. There's a lot of confusion in the media and online that the two are equivalent, or describing GATT-based systems as beacon-based, but that's a bit like saying that rugby and soccer are the same game, because you kick a ball to score goals. But anyway, what are beacons? Bluetooth Low Energy devices periodically broadcast advertisement beacons all the time. This is used for many purposes already, such as being able to find when a device has been turned on, or having devices that provide positioning information indoors, where you can't use GPS satellites. Apple and Google's Exposure Notification API also uses beacons. Phones with a contact tracing app would broadcast a temporary identifier using this same mechanism. These broadcasts are offloaded to the Bluetooth controller in the phone, letting the CPU sleep, preserving battery life. Meanwhile, the app periodically wakes up the phone's CPU to listen for other phones with a contact tracing app and records any temporary identifiers in an encounter log. This doesn't require any one-to-one connections and is data that devices are already transmitting all of the time. This and the minimal involvement of the phone's CPU makes the process much more power efficient. The disadvantage is that you can't transmit much data, at most 24 bytes, so your data needs to be compact. GATT systems are a little different. Most contact tracing apps deployed or proposed before the 15th of May 2020 currently use GATT, including those from India, Singapore, Australia, Alberta, Poland, and the UK. GATT uses one-to-one connections, and there are two roles, a peripheral and a central. An app in the peripheral role transmits beacons that say, I'm running the app, but unlike a purely beacon-based system, it doesn't contain any useful identifier for contact tracing. An app in the central role listens for these beacons and tries to connect to anyone nearby who is running the app. They then exchange an identifier, one-to-one, and write it in their respective logs. These apps need to switch between the peripheral and central roles periodically to make sure they found every other app user nearby. The only advantage of using GATT is that you can transmit much more data than using a beacon. Depending on the Bluetooth chip in your phone, the constant role switching can interfere with other apps used of Bluetooth. This includes medical devices like continuous blood glucose monitors used to manage diabetes. The biggest flaws with using GATT are scale and power usage. Even limiting your transmission to the same size as a beacon, there's a lot of back and forth communication, and this all occurs one-to-one. All of these steps require the constant involvement of both devices' CPUs, which consumes more power. If you have 3 people, GATT needs 3 complete exchanges to occur, A to B, A to C, and B to C. By comparison, using beacons, everyone's broadcast can be received by everybody else at the same time. Only the receiver's CPU needs to wake up because beacon transmission is offloaded to the Bluetooth controller. When this grows to 5 people, GATT requires 10 complete exchanges to occur, A to B, A to C, A to D, A to E, B to C, B to D, B to E, C to D, C to E, and D to E. While in an ideal case some of these can occur in parallel, it is still less efficient than using beacons, and packet count increases on a quadratic scale. All the while there's a risk that devices will move out of range before exchanges can complete. Now, given these problems, you might wonder, why would anyone use GATT for this purpose? And the answer is mobile platform restrictions. The regular iOS Bluetooth APIs don't allow apps to broadcast arbitrary beacon data in the background. This is likely because it is easy for developers of Bluetooth apps to unintentionally compromise Bluetooth and iOS privacy features if not used correctly. There are multiple examples of this problem in contact tracing apps on Android, but that's a story for another time. On Android, while its APIs permit it, both Android itself and vendor customizations automatically stop applications running in the background if you're not regularly using them. And in the ideal case of a contact tracing app, you'll open it when you first set it up, and then again only if you or someone you've been in close contact with has tested positive. So, in summary, GATT-based exchanges are one-to-one and require more steps and data transmission to complete an exchange, which scales badly and consumes more battery life. Beacon-based exchanges are one-to-many, which scales better and consumes less battery life but are limited in size. These factors make GATT-based systems inherently less reliable than beacon-based systems. iOS prevents backgrounded apps from transmitting beacons, and it's easy to use Bluetooth wrong in ways that compromise user privacy. And finally, no matter the mechanism, apps are not a silver bullet to solve contact tracing. You can make human contact tracers' jobs easier by keeping a diary of where you've been, how you got there, and who you've been in contact with. If you're interested in reverse engineering and reviewing contact tracing apps, you can find more information and join the community at covidsafe.watch. They've written much more about these apps, which has helped me write this talk. I'd also like to thank Sherelle Collette, Jim Mussered, Josh Driver, and William Brown for their feedback on the earlier drafts of this talk. Thanks for listening.